Welcome back, everyone. Welcome to our online and on-site participants. We are approaching slowly the last session of the Open Data Science Europe workshop. We have still 3 more lectures to see, and we will kick off this last block with another colleague from the ECMWF, Claudia Vitolo. She's a researcher at the ECMWF, and she will talk about the tools for the global wildfire danger forecasting. And with this, Claudia, I pass it to you. Keep it to 40 minutes and ideally leave about 5 to 10 minutes for questions. So please take over.
Okay, thank you very much, Tom, for the introduction. And hello, everyone. My name is Claudia Vitolo, as Tom said. You find me in a moment of transition, actually. I just a week ago, I started a new job. I am now a senior scientist at the European Space Agency Center for Earth Observations in Italy. But today, I'm going to talk about a work that I contributed to until last month when I was working as a researcher for the fire forecasting team at the European Center for Medium Range Weather Forecasts. The work is a teamwork. It's the work of a wonderful team that you can see here on this slide listed. And my talk will touch on a few resources in terms of data and tools, and I also will give you a glimpse on what research projects the team is currently busy with. However, if you want to hear more about wildfire danger forecasting, I invite you to contact Francesca Di Giuseppe, which is the leader of these activities at ECMWF. A little bit about me, just to give you a bit of background. I have a degree in civil engineering, a master in environmental management, a PhD in hydrology and data mining, and a lot of experience as a researcher for various university research centers and consultancies. In 2016, I started working for ECMWF on the development of multi-hazard early warning systems for weather-driven hazards, and then moved on and focused my research on wildfire forecasting only. And since a week ago, I'm now a senior scientist at ESA. But now let's start with a brief introduction. I will tell you what ECMWF is and what Copernicus program is. Okay, ECMWF is an independent intergovernmental organization that is supporting a number of member states and cooperating states. It's a research center, an operational service that works 24/7, and the main mission is to produce and disseminate numerical weather predictions to its member state. On the other hand, Copernicus is a European Union Earth observation program, which consists of a number of services, and within ECMWF, we have two of these services implemented: the Copernicus Climate Change Service, also called C3S, and the Copernicus Atmosphere Monitoring Service, also called CAMS. But ECMWF also contribute to a third service, which is the Copernicus Emergency Management Service, also called CEMS, for what relates to flood and fires. So the activities of both CAMS and CEMS services are both related to wildfires, but there is a distinction. While CAMS goals are to monitor the wildfire activities in real time and estimate fire emissions released in the atmosphere, what CEMS Fire does aims at providing fire danger forecasts to feed the European Forest Fire Information System, also called the EFIS, and the global counterpart, the Global Wildfire Information System, or also called GWIS. Both of these platforms are managed by the European Commission Joint Research Center, while ECMWF is only the computational center. So just to give you a little bit more background on Copernicus EMS, the Emergency Management Service is a service that aims at supporting the civil protection and humanitarian aid operations by providing information for emergency response and disaster risk management in terms of two things: on-demand mapping of emergency situations and early warning and monitoring of three weather-driven hazards, mainly floods, droughts, and forest fires. And obviously in this presentation, I will only focus on forest fires. But what do we exactly mean when we talk about wildfires? So there are a number of comprehensive definitions, but in summary, I would say that wildfire is an unplanned and uncontrolled fire that burns in wildland vegetation, often in rural areas, and there are different types. Wildfire can burn vegetation both inside the soil and above the soil. So we have ground fires, where typically what ignites is the organic matter within the soil, and this can be plant roots, for example. And it's very problematic because ground fires can smolder for a very long period of time. Then we have surface fires, which burn the dead or dry vegetation that is either lying on the surface of the ground or growing just above the ground. So fallen leaves or parched grass, etc. These are the things that fuel this kind of surface fire. And then we have crown fires. The crown fire burn the leaves and the canopy on top of the trees and shrubs. And while in general, I would say that the area burned by wildfire has declined globally over the past decades, it's very important to clarify that fire is now occurring more frequently and unfortunately severely in ecosystems that have historically rarely experienced fire. So think, for example, of the fires that occurred well above the Arctic Circle in 2019 and 2020. So as a consequence, there is an element of preparedness that is affecting how a wildfire can impact an area and nearby populations. So now moving onto causes, what causes a wildfire? There are a couple of categories of causes. The wildfires can be caused by human activities or natural phenomenon like lightning, and can happen anytime and anywhere. But for about 50% of the wildfires recorded, the cause is actually unknown. And when the cause is known instead, it is estimated that about 90% of the wildfire is caused by humans, and the other 10% is occurring due to natural reasons. So what we really know about wildfire is that it's driven mostly by weather, and the risk of wildfire increases in extremely dry conditions, and therefore it's important to track drought situation or, for example, high winds. So in terms of impacts, the wildfires can disrupt transportation, communication, water supply, can also release large quantity of carbon dioxide, monoxide, and fine particles in the atmosphere. And this is not simultaneously impacting the local weather and the large-scale climate, but is also leading to a deterioration of the air quality. And this consequently leads to a loss of properties, loss of crops, resources, animal, and even loss of life, human lives. So it is estimated that wildfires affected millions of people in the past decades, and unfortunately, due to climate change, things will very likely get worse because hotter and drier conditions are drying out the ecosystems and increasing the risk of fires. So what do we call wildfire danger? And let's start from saying that it is notoriously very difficult to predict when and where an ignition will occur. But when And once an ignition does occur, then it is much easier to determine how much a wildfire will grow. And this is because the condition to sustain a fire depend on three things. The weather, we said already that before, in particular wind, strong wind can favor fast-moving fires, hot temperature, lack of precipitation, and low humidity. But also, it's very important to map the availability of fuel, because without fuel, fire cannot ignite and cannot sustain itself. And also, topography is an important element, because flames burn very fast uphill and faster than they do downhill. So what do we need to remember is that wildfire danger is a measure of how dangerous a fire can be if an ignition occurs. Therefore, technically, this is a potential danger, and this is a concept that we need to keep in mind. There are several well-established systems that measure wildfire danger. For example, the Fire Weather Index system that was developed in Canada, and it's the most widely used worldwide. Then we have the National Fire Danger Rating System developed in the US, and the MacArthur Forest Fire Danger Meter, which is developed in Australia. And each of these systems generate a number of danger indices, where each index pretty much works in this way. The higher the index, the more dangerous the condition. So they are pretty simple to understand. Not that easy to interpret, but we will get into that later on in the presentation. Under the CHEMS fire activities, the global ECMWF fire forecasting system, also called GEF, was developed and made operational in 2018. And GEF implements all the three indices and calculates all GEF implements all the three systems, and therefore calculates all the related indices and calculates additional indices on top of that for statistical reasons that I will explain later. So GEF works in two modes, area analysis and the forecast mode. So for those of you that don't know what area analysis is a data set that blends together a modern forecast model with past observation. And the aim is to reproduce the fire danger conditions in the past with an homogeneous coverage over space, but also over time. And so GEF produces reanalysis data set of fire dangers, but also forecasts. And the forecasts are available in different versions and up to 15 days ahead, consistently with the ECMWF meteorological forecasts. The reanalysis of fire danger indices are available from the Copernicus Climate Data Store, or CDS, under a Copernicus license, while the forecasts are available in real time, but from the EFIS platform under a JRC license. So we need to keep in mind that the data licenses are different here. So in terms of production, GEF is a open source software on its 4th version now, and it's available under a Apache 2 license. GEF ingests grid in terms of meteorological inputs and outputs grids consistently with meteorological forecasts. So the grid is consistent. However, we have systems in place to convert the GRIB outputs into NetCDF for those users that are not familiar with the GRIB format. GEF is also an experiment-ready system, in the sense that experiments are really easy to run. We have strategies for running idealized conditions, and experiments can be run on demand quite easily. You can read more on the paper that is cited at the bottom of this slide. Now, the most widely used component of GEF is the one that generates the fire weather index, because it's also the index most widely used. And the system itself is made of 3 non-interactive fuel layers, and the schematization that explains the drying of the soil depends on both long and short-term temperature, humidity, and precipitation. Also, wind plays an important role because it controls flammability, and the combination of dryness and flammability produces a general index of fire danger that is called fire danger index. So just to give you an idea of what an FWI map looks like, this is the FIS website, and you can see the values are given into categories. Even though the FWI is a rating system, so the number goes from 0 to infinity, although values above 100 are very rare. The FIS they made a decision to visualize this information in terms of categories for simplicity, I would assume. And those categories goes from low to moderate, and then all the way to extreme danger. Those categories are fixed, so there are fixed thresholds that define those categories. And for instance, the and also you can see the photos here on this slide. The photos show the value of FWI in terms of absolute value and the corresponding area on the map. And basically you can see that the FWI below 20, for example, corresponds to fires that interest only the grounds, the area near the ground that are fairly easy to extinguish, while higher values may correspond to those very destructive fires that are very difficult to contain. This is a bit simplistic, but I just added some photos there just to give you a sense of what this number means. But there is a problem, because categorizing danger using fixed thresholds can lead to several problems. So say that the FWI equal high danger has not the same impact everywhere. So for example, think of FWI, the FWI is equal to very high danger, and this corresponds for in some particular circumstances to a temperature of 30 degrees Celsius. So you can think the 30 degrees Celsius may be very common in an area like Mediterranean countries, where during summer, for example, but may not be that common in an area like Sweden. So there are categories that are never reached, and for example, in Nordic countries. And also, we need to remember that forecasts do not provide any information about the probability of ignition. And if an FWI is forecasted to be extreme, it does not necessarily mean that there will be a fire. For these reasons, and for also other reasons, these indices need to be interpreted by a domain expert. So now I would like to explain you why the campfire activities are so important, and what the added value is of such a system compared to the traditional way of monitoring fire danger. So monitoring fire weather or fire danger, here I use them as synonymous, can be done using weather station data. So see, for example, the left panel of this plot here. Here, this plot was generated for the fire event in Pedro Grande in Portugal in June 2017. And you can see the blue shaded area is where the fire actually occurred, and the pixels are actually fire radiative power from satellites. The dots are instead the locations of the weather stations, and they are color-coded based on the severity of the fire danger calculated locally. And you can see the area was on the day was categorized as at extreme fire danger. But the problem with this kind of solution to monitor fire danger is that the information is only available at discrete locations, while if you use a CAMS fire approach, you have a gridded layer. So basically the information is available everywhere. There are no gaps. And also the information from extracted from weather station is only available for the day, the current day, the day of the observation, while CAMS fire can build on weather forecast and forecast fire danger up to 10-15 days in advance, at least for the medium range. Okay, but at this point you might ask, okay, but how reliable is it? How reliable is CAMS estimate compared to the local estimate? So in order to compare CAMS estimate with the local one, I invite you to look at the second plot. So the second plot is basically a point inspection in the location of the weather station of the CAMS file of the FWI layer. And you can see the FWI was estimated to be at very high danger. So here you can see, admittedly, a slight underestimation, but this is normal for when you compare gridded information with the point locations. But the real advantage here is this has the estimate, the FWI estimate using Jeff was made 10 days in advance. What was made 10 days in advance. And this is important because this would give fire authorities enough time to prepare to a major event. They could use these forecasts as a trigger to take action and prevent a fire from happening, or maybe control a fire that has already been ignited. So in general, I would say that there are lots of ways this kind of system could be used and is useful. So for example, you can think of early warning systems because they can warn local authorities days in advance. You can use it as a decision making tool because you have the time to allocate resources on the ground, and you can use it for scientific reasons because, for example, the reanalysis products go 40 years back and are particularly useful if you want to look at trends over space and over time. So yes, it's a very, very useful tool. So now let's dive in a little bit more into the data itself. So this is a bit of a wordy slide, I apologize for that, but mainly what I want to, I wanted to give you all the information in one place, so maybe you can use this slide as a reference in the future. So ECMWF is generating 3 types of data products. A climatological data sets, so based on ERA interim and ERA 5 reanalysis. These have different spatial resolution, but the latest one is the one based on ERA 5 that is characterized by a 28 kilometer resolution. It's available 5 days behind real time, and it uses the forecast model cycle 41R2, which was developed in 2016. So fairly recent. Then we have the category, the data products related to medium range forecasts, and these are issued daily at local noon, and we will get back to this point later. It's using at the moment the IFS cycle 47R2 that became operational in May 2021. And there are different data products within these categories. We have a deterministic high resolution forecast made, obviously it's deterministic, so one realization with a spatial resolution of 90 kilometers and 10 days lead time. Then we have a probabilistic product made of 51 ensemble members, which has got a lower resolution, but still very impressive, 18 kilometers horizontal resolution, and 15 days lead time. And then we have a number of statistical indicators that are calculated on top of our forecast and are anomalies, ranking, extreme forecast index, and shift of tail. I will tell you a little bit more about those later on. And then we have a number of experimental products. We have the hourly FWI after 3 days, and the probability of ignition from lightning. This is very exciting, and I also will tell you about that later. And then finally, we have the latest category that is relates to the seasonal forecast. This is currently this has been developed, and it's currently been validated in collaboration with NASA. It's based on ECMWF seasonal forecast S5, and it's going to be issued monthly with a lead time of 6 months. One thing to remember is that the climatological data sets and the seasonal forecasts will be available under a Copernicus license, most likely both on the Climate Data Store, while the medium range weather forecast is available under a JRC license. So if you need forecast in real time, you will have to contact the EFIS team. There is a data request form on their website, and you need to make a request for data that way. So now moving on to what's available in terms of training. So ECMWF runs a number of training activities, and for those training activities we use sample data sets for past events, but we also we make them available in a public data repository, in this case Zenodo Wildfire Community. In there you will find a number of data sets for past events, but you will also find the past version of the reanalysis, those versions that did not make into the Climate Data Store because they were still being validated and tested. So you can use them for educational purposes, basically. And then I invite you also to have a really look at the reanalysis. The reanalysis dataset is very, very important for a number of scopes. So you would use the reanalysis to identify fire-prone areas, climate teleconnection, fire regime changes, and fire season modification, and loads of other things. So we have written a paper, and there are some examples of that in the paper. So, and now we'll tell you a little bit more about the probabilistic products. I'm not gonna go into the statistics or the equations here. I just tell you that those products are basically indices that tell you not only how intense the fire is in that particular time or in that particular place, but it tells you how anomalous those conditions are compared to what happened in the past. So they are very, very important for forecasters, but also you need to know that interpreting those indices, it can be quite tricky. And this video, I'm going to show you a video now in which I'm going to show you how the information provided by different indices can be confusing. So I really encourage you to interpret those indices with the help of a domain expert. So I'm gonna now play the video. Here I'm gonna use a web app that is internal to ECMWF and member states, which is called DC chart. I'm gonna load two indices, the FWI and the EFI, which is the extreme forecast index. And for example, I'm gonna stop it here for a second. You can see here, I'm loading the FWI first. And according to the FWI layer, the south of Spain looks like it's in a pretty high danger condition. While the south of England and the north of France are not that concerning, right? They are green. Now let's resume the video. I will then load another layer, which is the Extreme Forecast Index, which is one of the probabilistic products I mentioned just one slide before. And you will see the situation changes completely. So you have now the south of Spain seems no longer, it seems that the conditions in south of Spain are not longer that concerning, but the conditions in the south, England and north of France are now more anomalous than what it usually happens at the same time in the past years. So, in this video, really, what I want to prove with this video is that you need a domain expert. The information can be confusing, can be really misleading sometimes, so you do need to interpret it right. So I think the video stopped there. Yeah. Okay, so I have a slide now on the seasonal prediction products. The seasonal fire danger predictions are currently also experimental. The plan is to issue a monthly forecast of FWI anomalies with 6 months lead time. And this type of product is very important because it allows to predict important changes in fire danger conditions months in advance, and perhaps this can trigger long-term, short-term adaptation measures. And now I want to talk to you about the experimental products. So just to give you a bit of background, the medium range weather forecast, I already mentioned that before, but I'm not gonna repeat it now, is issued daily. And it is basically a mosaic of what is expected in terms of fire danger every day at local noon. So it's a mosaic of the different area on Earth, and you can see what could happen at local noon everywhere. So the assumption is that the worst conditions for fire occur around noon. And this is an assumption that is very convenient because it makes the calculation of fire danger very efficient, but it's not necessarily true. So we ran some experiments and noticed that in some areas in Europe, the worst conditions occur in the morning, for other areas occur in the afternoon. Therefore, soon ECMWF will release 2 new data products, the maximum FWI of the day, based on our reruns, as well as a map of the time of the day at which the maximum FWI occurs. And it is important to mention that the entire development of these 2 data products was triggered by the feedbacks from Meteo France, which is a meteorological service in one of our member states, France. And this highlights how important the collaboration with member states is for ECMWF. There is one more experimental product I want to tell you very briefly about, and this is the last product is the result of a recent research that was carried out by my colleague, Ruth Coughlin. The key idea is that the dry lightning are more likely to ignite a fire than the lightning associated with heavy precipitation. It sounds simple, but it's a very important concept. And Ruth built a machine learning model that predicts wildfire ignitions from lightning forecasts using fuel availability and soil moisture content as predictors. And the output is a map of probability of ignition due to lightning. The first results are pretty encouraging, and this is now triggering further research in the area. So now very briefly on the tools. So the very first resource I suggest you to look at is the Copernicus Emergency Management Service website, because there are 2 tools related to wildfires to explore. So the first one is the rapid mapping tool, where there are reports of events that occur in real time, and users can get information on the cause of the event, whether a fire was caused by natural or other sources, for example, arson. Or you can also get information about the extent of the area that has been affected. The second tool I've already mentioned is the European Forest Fire Information System that provides an overview of the current situation in terms of fire danger in Europe. Beside this EFIS, we also have a global platform that's called the Global Wildfire Information System, or GWIS. And EFIS and GWIS are two systems that present very similar information, but for certain aspects are complementary. So the platforms are both free and openly available, openly accessible. They provide daily fire danger forecasts for Europe and globe respectively. And along the forecasts, there is also a monitoring component that looks at active fires and burned areas based on satellite imageries. MODIS and VIRS are the one used for detecting the area. But the perimeters are then refined using Sentinel-2 observations. So on EFIS, you can also find statistics of wildfires by country, while in GWIS provides information on fire emissions. So in this case, in this sense, they are quite complementary. And then I would like to point you to the Copernicus Climate Data Store, which is obviously a data store and is openly accessible. It's an application that you have to access, although it's behind the authentication layer, so you have to register an account. It includes a toolbox for pre-processing of data on the server side, and it's proved to be very useful to those users, to several users, because users no longer need to download a large amount of data if they can process it on the toolbox and only download the resulting maps, plots, and summary statistics, whatever they need. Then we have, in terms of software, the Jeff model itself is open source and it's available from an open data repository or open repository that I link here. We also have another software which is more used for post-processing of fire danger data, and this is for the R statistical software, so it's a Caliverar package. It's also available under an Apache 2 license, and it's also available on CRAN. There are some vignettes and examples that they show you the functionalities of this package. For Python users, we also have Jupyter notebooks that perform pretty much most of the operations that you can do with the Caliverar package. And this is what we mainly use. We have mainly used in the past for training. And this is my last slide. It's simply a summary of references for you to explore. And with this, I would like to thank you for your attention. And if you have any questions, I am happy to answer.
Thank you, Claudia. Thank you so much. This is really an in-depth review of your work, and fantastic that all this data is available, including the data stores that you call. So the floor is open for questions. I'm just looking if there's any question in the chat. If you have a question, post in chat. And I'm looking here also at the conference hall. You don't have a video on the people, but we're about 25 people at the site, and then 25 people online. So we're looking for questions for Claudia. Maybe I will kickstart, Claudia. So we have there's this new Sentinel missions, and they are much higher resolution, like Sentinel-2. Do you think for example, Sentinel-2, do you think it could be used to inventory actually actual fires, and then use that as the in situ data for reanalysis of your models? Or how do you use the other EO data sources to, let's say, quantify actual fires?
Okay, the Sentinel-2 data is currently already used for refining the perimeters of burned areas from fire. So it is actually used. In terms of assimilating this information into the reanalysis model, I'm not entirely sure it's in the plan, but it is. I'm no longer part of the team, so I'm not entirely sure what the strategy is in the long term. But for this kind of question that are related to the future developments, I would suggest you or any other person interested in the audience to contact Francesca Di Giuseppe, which leads the activities and is more up to date than me on.
Connected question. So there's a new system coming up. We heard from Raymond Slaughter from the Dutch Space Office. There's a new satellite coming, the thermal, thermal with the thermal sensors and multiple thermal bands. I forgot the name of the mission, something LSD. And I think it's a 50-meter resolution or something. So how much do you think that's going to revolutionize monitoring fires and fire danger?
Oh, I think it's very important that satellite missions develop and produce data that is more at finer resolution, etc. For example, we were looking at the work for detecting ignition, for example. That would have really it would have been very good to have information about biomass, and this is going to be available soon with the newest satellite mission. So I'm sure there is a lot to do and a lot that could be done. And yes, again, I invite you to contact Francesca Di Giuseppe.
There's a question by Piero Campolani.
Yes.
It says you also have a background on multi-hazard analysis. Are there any online tools for multi-hazard risk zonation?
The one I worked on is not open, so it's developed to be commercialized, and so we developed a
and what's the name?
Concept.
What's the
It's
name?
the Anywhere platform. It's called Anywhere
Okay.
platform.
Okay, but the open data one, you're not aware of any?
No, not aware.
Okay. With this thing, we have to stop. Thank you so much
Thank you for having me.
We're very sorry you couldn't come here, but we understand and we are flexible this year. It's a hybrid conference. You see about half people online, half at site. But we're having, I just want to tell you, we're having a good time here, and we are interacting, and it's nice to be back to school. And with this, I would like to thank you one more time, and good luck with your work and the transition.
Thank you, and I wish you a nice rest of the workshop.
Thank you. Bye. We stop now. We stop. We move to our next presenter. As you saw from the program, we have a one presenter which is not in the printed program, but we are very happy to have Denis Massillonas, who is the university lecturer here at the Wageningen University, so very close by. And he works in the remote sensing and GIS lab of Professor Martin Herold. And so he's a really hands-on person, a real data scientist, and he's been involved in building global land cover products. And also he's developing a time series analysis tool, and he's going to talk about the BFAST Lite. It's a new implementation of BFAST. I think Leandro mentioned it. And so we are super happy to have with us Denis, and I will be opening his talk. So Denis, please, the floor is yours.
Yeah.
Keep it 15 minutes plus 5-minute question.
Okay, thank you. So hello, everyone. Yes, I'm Denis Massillonas from the Laboratory of Geoinformation Science and Remote Sensing in the University of Wageningen. And today I'm going to be talking about automated global land cover disturbance monitoring using BFAS Lite. And I will explain to you what that is in a minute. But first, yes, so Tom already mentioned what I'm working on. Just as a very short summary, I'm both a PhD candidate and also a lecturer at the group. And my thesis is about global land cover mapping and updating using time series analysis. And I'm involved in the. Yeah.
Could we get the slides, please?
Sure. Yes.
Here and
Screen. Yes. Yeah.
Sorry.
Yes.
Controller.
Okay, now you can see. Yeah, thanks. So yes, so I'm involved also in the Copernicus Global Land Services land cover project. And what I'm presenting today also was used in making the global land cover product at 100-meter resolution. And specifically, my part was looking at how to do the updating from one year to another and making it, improving it. And that's not the only thing that I work on. I'm also a lecturer and I'm responsible for the geoscripting course in our university, where we teach master students about how to do scripting for spatial data analysis. And all of the materials are also open and online. So if you want to learn even more of scripting things than you have learned throughout this week, then feel free to see also here. I'm also working on another project, Sensico, which has to do with both time series analysis as well as sun-induced fluorescence to detect whether there's plant stress in the field. And I'm also involved in the OpenEO project, which is a project about making spatial data infrastructures for handling large amounts of data, which I will mention a bit more later on in the presentation. But what is most important today is the BFAS package maintenance. So I'm the maintainer now of the BFAS package, and today I'm going to talk about the latest update of the package, version 1.6, and what new things you can find in it. So the background is land cover change detection for updating land cover maps. And the issue that you find if you just try to create land cover maps year after year is that you will have a lot of spurious changes because the data has slightly changed between the different years, and now the algorithm thinks that it's a different land cover class than it was last year, even though the change is really small. You can do several things about that. You can do expert rules to, for example, rule out which transitions are unlikely or impossible. What you can see here on the right is an unlikely land cover change. It is a change from urban to water. In other words, flooding. But it's not likely to persist for an entire year. So usually we can rule out such changes as erroneous. But you can also do some more advanced things, such as doing time series break detection to constrain which areas have change in the time series and which areas don't. And if there is no change, then probably we don't need to change the land cover class, and we don't even need to classify it for the next year. And there are many options for the algorithms that can do such a thing. And today, I will be talking about a new addition that we have developed in our group called BFAS Lite. But to explain how it works, I need to first explain how BFAS, the original version, works. And it's an algorithm that takes as an input a time series of a vegetation index. And it decomposes it into three parts, because any kind of vegetation index, as you see at the top here in the graph, is the original vegetation index, can be decomposed into seasonality, which you can see right below it, and trend, which you can see below that. and as well as the unexplained noise, of course. And this algorithm was originally developed in 2010 by my supervisor, Jan Wesselt, and generally it works fairly well. This is the way that it works, called BFAS because it's short for breaks for additive season and trend. And it uses the R function STL that does automatic decomposition of time series into these three different components that I mentioned. Then each of the components, well, except for the noise, because we don't really care too much about the noise, but both the seasonality and the trend are subdivided into these kind of stable segments. So these are the parts of the time series where nothing substantial has changed, which means that within that segment, the model parameters stay constant. Of course, there is one thing that, since we decompose the time series into seasonality and trend, the fact that we have breaks in seasonality or trend will also by itself influence the time series that we see. So the algorithm works iteratively, and it also, on another iteration, sees whether if we only take the stable segments, whether they can further be subdivided in a different way. So it does it iteratively until convergence has been reached and no further decomposition makes any difference for the results. Afterwards, it detects all of the breaks in the time series of both seasonality and trend, and then it specifies, of course, whether the break is in seasonality or is it in trend. And that way we can know whether there was any change in the time series and at which time within the time series the change happened. And we can detect also multiple changes in the whole time series. So now what's the newest development? That's BFAS Lite, where instead of having to do this kind of complicated decomposition and iterative processing, BFAS Lite is faster because it can detect breaks in all of the components all at once in a single pass. That has several benefits. One is that it's an order of magnitude faster than the original BFAS implementation. And that is in addition to speed improvements that have been made in the package also in version 1.6 by porting some of the code that was originally in R to C++, which made it another order of magnitude faster. That's work that was made by Marius Appel, who was also in this conference. And also another thing that it does no longer use STL. And what is nice about that is not only that it's much faster because of that, but also it can handle missing values. Because the original STL cannot handle missing values since it needs a time series with a regular interval. Whereas BFAS Lite just works with a simple linear regression, which does not need any regular intervals. And we also have a lot more tunable parameters for BFAS Lite as opposed to the original BFAS. So for example, we can decide which harmonics to use, whether to use seasonal dummies or use our own external regressors, which all allows fitting the data better if we have more information to decide which model fits it the best. And so how does it work in practice? Well, as I mentioned, it's a piecewise linear regression. Basically, if we take the vegetation index time series, we first have a question. So if we want to know when one break happened in the time series, where would we put that break? What it does is it does some optimization, and it tries to put the break in a different location, and then it finds basically what is the best combination so that the residual sum of squares is minimized, so that the whole time series is fit by the model the best if we put that one break in the time series. Then the algorithm checks what if we want two breaks in the time series, not one. It does the same thing, minimizes residual sum of squares, and so on and so forth with more and more breaks until the maximum is reached. And in the end, we get a triangular matrix, which tells us, given a number of breaks, how well do we have of a fit for our model to our data. Of course, then we have a triangular matrix, and we still don't know how many breaks there actually are in the time series. So what we get in the end to automatically detect it is that we use an information criterion. So we know that if we increase the degrees of freedom, that is, if we detect more breaks in the time series, surely our model will fit better because we allow more changes in the parameters. So we have more degrees of freedom. So to avoid more breaks being better always, we have to penalize for each of the degrees of freedom. And we can use different information criteria, for example, the Kaik information criteria, but that one tends to be very much overestimating how much of the breaks that we detect. BFAS, the original BFAS used BIC, but it's also often too weak. It still detects too many breaks. So we have now implemented LWZ, which is an even stronger criterion, which seems to do better at detecting actual breaks and skipping everything that is not such a significant change. And of course, you can choose which one to use as a user. So just as a bit of an example, this is a time series of a vegetation index, and you can see that it goes up and down, and it's quite noisy. And you can see the trend component specifically. And this is the difference that using LWZ makes as opposed to using BIC. So in LWZ is in black straight lines in the top graph, and BIC is the straight line, black straight line, and LWZ is the teal straight line. And you can see that generally they agree quite well together. The only difference is that according to BIC, there is a break in 2013. And LWZ thinks that, well, it's probably not a big enough break that we should actually detect it as a break. You can also plot it in a different way. So to see why the information criterion selected this amount of breaks by plotting what's the information criterion value versus the number of breakpoints that it's detected. And then you can see why it selected this. So this is nice because it gives the users flexibility so that you can check if you have an area with very common changes, then you can use BAC. If you have an area where change is relatively rare, then you can use LWZ. And you also get these statistics so you can decide better based on that, whether one model fits better or another. Another new thing in release 1.6 is the R-squared. So you know in total how well does the model fit the data. And you also get the magnitudes for every break. So even if it decides that there is a break, you can still decide on whether the magnitude of the break is big enough that you should care about the change. Because if it's small enough, perhaps there's no line cover change either. And there's also different ways to estimate break magnitudes, so you get quite a lot of statistics out of it. And there's also a parameter to customize the number of seasonal dummies if you use seasonal dummies instead of harmonics, which also allows you to fit the seasonality in ways that you cannot really do with harmonics, because perhaps the seasonality does not follow a harmonic pattern. So what's next? What we're working on now is trying to figure out what all of the parameters that we have introduced, how much of an effect does it have? And also how well can we detect line cover change in general to begin with? And we're using a reference data set collected by both IASA and Wageningen, which is quite a large data set covering the whole world that you can see on the right there. And we're trying to find out which parameters are optimal for detecting line cover change for the world. And we found that basically using this LWZ criterion definitely helps with reducing the number of false changes that the algorithm detects. And it's more in line with reality. And in the end, we still found that just using BFAS alone is not really sufficient to detect line cover change. that we also need to combine that with classifier output and perhaps combine several models together so that we can detect land cover change specifically and not just some disturbance on the ground. And I also published a paper recently, specifically detailing a bit more about a comparison between the original BFAST, BFAST Lite, as well as BFAST Monitor on detecting global land cover change, which you can find in at the link below. And I will also show the link a bit later. And the next step will be to work more on other implementations of BFAST, because it's an R package at the moment. But we also have a package on Python, as well as an implementation in Google Earth Engine, which allows to scale up the algorithm to even larger areas, which is also very important because we also want to scale down to 20-meter level. So for land cover mapping, for example, using Sentinel-2 is much better than using low resolution imagery such as ProV that we were using before. But that also means a 25-time increase in data volumes. And that's for mapping itself. But change detection, in the past, we used MODIS, which is at 250 meters. And now we want to move to Landsat, which is at 30 meter, which means that there's a data volume increase of 70 times. So that really requires optimizing the algorithm quite a lot. So the original BFAST would not be able to make it, but BFAST Lite has the chance of actually being fast enough to do it. And we also want to make use of some Sentinel-1 data for gap filling in the future. So that's for the upcoming releases for the Copernicus global land cover. And we also are working a bit on a new development for the BFAST algorithm to create a kind of a supervised variant, because right now BFAST is unsupervised, it just gives you an output. But if you can train a bit on what you actually want to do, then it might give you a better output. And the idea right now is to do that based on deep learning, perhaps recurrent neural networks, and combine that with the Python version, which should be fast enough to be able to do the task. And what it would do is that it would automatically determine the vegetation index that is optimal for detecting a particular change that you're interested in, and also do automatic parameter optimization, which is also useful considering all of the new parameters that we have introduced into the algorithm recently in the version 1.6. And finally, I wanted to mention that we also want to make an implementation available on OpenEO. So OpenEO is a framework for handling large amounts of Earth observation data, which you can access using a client. We have R, Python, and JavaScript clients. And with that, we can also port these scripts to different backends. And the backends are optimized by themselves, and they have local access to the data, so you don't need to download all the data yourself. The nice thing about it is that you can also run user-defined functions, and BFAST is like a user-defined function. So we're currently working together with Vito to implement BFAST Monitor specifically on their platform so that users can also very easily run it by just going to their marketplace, defining an area over which they want to run the algorithm, and then just downloading the result. So that's about it. If you want to try running BFAST Lite yourself, we have a tutorial about that. It's the first link that you have here, and there's also a QR code if you want to follow it. You can also run it directly within our Markdown file so that you don't need to copy paste the commands. And as I mentioned, there's also a paper that I just recently published with more details about how the algorithm works and the comparison with other algorithms, including BFAST and BFAST Monitor. So if you're interested in learning more, please follow the link there. And there's also another QR code if you are interested in that. And that's all for today. And thanks for your attention. If you have any questions, don't hesitate.
Thank you for the presentation. It's nice to see the improvement in the detailed line. And you mentioned that now we're thinking how to and working how to educate people on the iOS solution data and stuff. So, I would like to ask you how you can really like run on a lens app. So because now we have we can see that we have the possibility to run using not exactly the data, but focus specifically for you what are your plans to actually run on a lens app data, because now lens app data it much more you will have more gaps and so it's more stable. So the question is more related with that.
Yeah, well, that's true. We will need to try and see how well it works on Landsat data, but generally, BFAST, the original BFAST, has been used on Landsat data quite extensively, and BFAST Lite specifically makes it even easier because it does not rely on interpolation, which is a big issue in the original BFAST. Since it just uses a linear regression, it should be fine for it to detect breaks. The fact that Landsat has a bit less temporal resolution simply means that BFAST Lite will not be able to detect breaks as precisely in time as it could with, let's say, MODIS data. But that's usually not a big problem, specifically for land cover mapping, because we update land cover maps anyway just once per year at the moment. If we needed to go into a bit more frequent updates, then we might need to think about alternatives. But so far, for at least the Copernicus Global Land Services project, it should be fine.
Okay, let's see. There's more questions. There will be a check. Can you look in the check? But no, okay, just the bottom. No. Any more questions? I wanted to ask if you can do the user defined function. Let's say for R users, can you make a function in R and then use Google Earth Engine? Is that possible?
Not directly with Google Earth Engine, because Google Earth Engine in particular does not support user-defined functions at the moment. So it's supported by specific backends, such as the Veto backend, and there basically the package needs to be installed on the backend to be able to use it. But that's not a big problem because you can just ask the developers to install it, and then you can just run any kind of R code that you like. And you get as an input a data cube, you just handle it as you wish, and you output also a data cube.
And what's the cost of the Veto backend?
Yeah, at the moment it's under development. So the marketplace is going to be put online at the end of the year. And then they will actually decide on the costs and so on, but they haven't decided yet about that because it requires some more insight into how much it actually costs them to run it.
Okay, thank you. We have to finish the workshop. Yeah. Thank you so much for coming and presenting.
You're welcome.
And yeah, it's great to see improvements, and it's been good also to meet the people that were actually talk to travel and in person.
So we are here for the last session. And this is just before the closing. We will have a very short announcement. And colleagues have connected from Belgrade and from Romania. So as you know, we have made, let me just turn this on. As you know, we have made that in the project, we have made data, we have made software, and we have also made that data portal. And in the GeoHarmonizer project, we would like to use this opportunity to now really especially thank to the people developing the data portal, which is a team in GI Lab in Belgrade, and also TerraSigna did development, Claudia Ifrim. So they're both connected, and we are very happy to give them the award. We're just very sad that we couldn't give them award in person because they couldn't make it here to the conference. So they're going to connect remotely, and they're going to give a presentation. Let me just share my screen before they start. So Luca, are you connected?
Yes, Tom, I am connected.
Okay. So I think Luca will first present, but let me just, I will just share my screen because I want to show you the GI Lab. It's a company in Belgrade, as I said, and they develop lots of backend and front-end solutions. But we would like to especially award for their especially creative and hard work. We would like to award Ognjen Antonijević and Luka Glušica for their contribution to the Open Data Science Viewer. They did most of the heavy work, and it was really, it's so fast and it's so impressive that we are really impressed. And so we would like that you give us a demo of the newest Open Data Science Viewer. So I pass now the screen to you, Luca. So please share your screen and give us show us what the Open Data Science Viewer can do. Just try to limit it, please, to 10-15 minutes.
Okay, just a second. Okay, can you see the map?
Yes, we see your screen.
Okay, great. First of all, we are very honored to receive this award. It's a kind of recognition and appreciation for the work that we've done in the past, and especially on this project. We are very thankful to all the partners on the project for their contribution and involvement, and for their trust, and for giving us the opportunity to work on something that we love. So let's start. Actually, first, a little bit about technical background and how the system is built. I would like to leave the floor to my colleague briefly before I start with the live demo session. Ognjen, can you please?
Yes, thank you. I agree with everything that Luca has said. I want to only mention quite briefly that the system consists basically of 4 services: the front-end application, the API that is serving point queries and all the relevant layers that you will see on the front end, the geo server accompanied by with the Postgres database, and the geo network that is holding the metadata for all the layers. These services are split into master and development server, and we here have kind of a hybrid architecture because GeoServer and all the big data that we are serving is on a dedicated virtual machine, and the front-end and API and GeoNetwork are in the cloud. And aside from these services, we have a Rancher and Prometheus for monitoring, and Nexus for storing all the build artifacts and so on. And I want to thank also a huge thanks to colleagues from Mundialis who helped us build this system. So this is all from me. Luca, you can continue.
Okay, thank you. Yeah, so a little bit about this data viewer. It's built using the modern JavaScript library for development of user interfaces called React. It's a good solution when you want to have a maintainable component structure, and if you want your application to be scalable over time. Also, the map that you see here, we incorporated it into React application by using open layers. We see open layers as the best solution for visualization of spatial data. There are a couple of reasons for that. One of the reasons is that open layers is the most comprehensive and well-documented library comparing to its alternatives. Basically, with core open layers package, you can cover pretty much pretty much every use case that web cartography requires. So also it's very GIS oriented. It has fully integrated web ODSE web services and standards, and it provides a high level of customization capabilities in case the use case is not applicable for the using only the core OpenLayers package. So let's move on to the live demo demonstration. So as you can see, most of the functionalities are on the right side. So you can see base map switcher. You can switch between different base maps here. Then all the data sets, some of which you witnessed during this conference, are presented here. You can select them manually, or you can search for them in this text field. So of course, opacity control. And of course, for some of the layers, we also have uncertainty toggle here. So you can see the uncertainty map of the selected layer. And of course, we also integrated the web feature service for training points, but they are available only at higher zoom levels because of the performance. Also, we used, just a second. Oh, here they are. We used some OpenLayers clustering capabilities in order to group the training points which are close to each other. So if you click on the point, you get the attributes for the selected point. And also if you click somewhere else, if the points are clustered, the first functionality is to break the cluster, and then you can select the actual point. So that's also integrated. Of course, there is a support panel here where you can see the issues and suggestions from the community. Of course, Twitter account. You can also share. We actually track multiple parameters in this application, such as selected base map, layer, zoom level, center of the map, opacity, and so on. And basically, you can copy this URL and send it to someone, or share it via social network. That's also an option. Of course, some shortcut keys to help with user experience. But the most interesting tool, in my opinion, is the comparison tool, which was developed as a custom solution using some of the OpenLayers capabilities. So we can compare two layers or the same layer with different time variables. For example, we can compare this land cover here with the land cover better spatial resolution, and use this vertical line to track the changes. So of course, for some of the layers, you can use this timeline slider to browse them through time. For land cover, it's a yearly temporal extent, so you can see through all these changes. And that is pretty much, I try to keep this short. That is pretty much the whole overview of the features.
There's also 3D view on data through Cesium.
Yeah, we also have two 3D components, one of which will later Claudia present, and another one is Cesium globe. So basically, just a second, yeah. You can toggle it and see the globe and the terrain details. And of course, perform all the functionalities same as in the 2D viewer. So this is pretty much it from my end. I would leave the floor now to Claudia to present her 3D component that we also integrated into
Thank
this.
you. Yes, please, we can switch to Claudia Ifrim, connecting from Bucharest, I think.
Yes.
She's a developer, and she did also amazing work on integrating, you know, the cesium it's open source, but it has limits. So we thought we want to have a diversity, and we also implemented the NASA Whirlwind, which is genuine open source. So Claudia, please, can you connect? Can you please?
Yes.
The development you made? So
For
Luca, for screen sharing, please.
You can share. You can continue to share your screen, and I can just talk. Just select the new 3D viewer in NASA.
That's also fine.
We have the same functionality as Luca presented before for 2D and cesium 3D globe. In the right side, we have all the layers, background maps, and we can also have the uncertainty points and the training points displayed. All the functionality are the same across all the viewers. We used the Whirlwind because open source globe that offers JavaScript API it's easy to be extended and develop custom features that were needed for the project. And it also has some improvement in the performance. And that's the main reason we also introduced Whirlwind. We support GeoJSON formats, KML, WMS, open protocols as WMS and WTS. And all the data, it's the same as on the other viewers. So the only difference is the performance, that it's a little bit improved compared with the 3D cesium option.
Maybe Luca,
And
you
I
could zoom
think
in. You could zoom into some place so we can see the rendering of the terrain. Yeah, please continue, Claudia.
We also have the time slider, and we for improving the loading time, we also cache these layers. Only the first time it's a little bit longer, the response times, but after that, if you go back, yeah, you will have a smooth response from the layers. And I think that's about all we have developed in this application. If you have questions.
Thank you so much, Claudia. We don't see you. I don't know if you have a video. Maybe if you could turn on video. Yes.
Yeah.
Thank you so much. And also, it's very nice to see. You know, this is a European project. We are participants from different countries, and it's nice to see. You know, you guys never met, and now you build up an app which is integrated. You develop different modules independently, and then you integrate it into the same app. And of course, you had a lot of online meetings and things, but it's a really success. It's a success of a European project to have two groups from different countries developing different modules, and these modules being seamlessly integrated. So congratulations on that. And our media office, Valentina, will interview next week. She will make an interview with you, and we will write a post about your work, and you will be announced also on all our media channels next week. So congratulations on winning the award, and it's really impressive work. And we are now open for other groups to, if they want to publish their data as long as it's European coverage and as long as it matches some minimum requirements like the open data license, complete metadata, and cloud optimized GeoTIFF as a delivery format. If some group, especially the people that are following online, if you are in possession of, if you're producing spatial temporal data for Europe, especially if it covers the period 2000-2020, we will be happy to host your data, and it will be available directly in a viewer like you see here, and you will be able to basically communicate your applications with potentially hundreds of thousands of users. So thank you one more time, Claudia, Luca, and Ogi. Congratulations, and thank you for your hard work. And there might be bugs, there might be problems. So if anybody experiences an issue, the easiest thing, as you see, there's a support page on GitLab. The easiest is that you post a screenshot and you put a little description of what the problem is. And Luca and Ogi and Claudia, they will try to fix as soon as possible. So thank you so much. We can now close the workshop. So it's official closing time, unless there's some questions to Claudia, Ogi, and Luca. Are there any questions, maybe? It's a Friday afternoon, and people are getting slowly, I think, tired, and also they're with their mind on our little celebration on the terrace at OpenGeo Hub. So, there are no questions for you, but one more time, congratulations. And with this thing, I would like to officially close the Open Data Science Europe workshop. So it's officially over. It's been 5 days of content. We had 2 days of training sessions with I think it's about 60 people, and a conference was also about 60 people, from which, well, actually a bit more. There were a bit more people following online. There were a couple of lectures with about 40, 50 people online. So it was maybe a bit more people in the conference online than in person. We had a lot of cancellations. We're very sorry. Also, you guys couldn't make it here. It's still complicated times. It's complicated times to organize, but many people tell me they are still happy to be here and to interact and to be able to talk with people normally again, not just through screens. So it was. We are very happy. It was really a success, and I would just like to thank also my staff, my colleagues, especially Claudia and Ryan, and also all the staff. The two Chrises and Carmelo and Leandro and Martijn. I would just like to thank my staff. You can imagine they work very hard, also months before they started. So we did a lot of work. It's always a lot of work to prepare a conference, and especially when it's a hybrid, then it's a lot of work, and it's also a lot of improvisation and uncertainty. But we made it, and remember, next conference will be next year in June in Prague. I already announced it. So it will be in Prague. It will be hosted by the CTU Prague, the Technical University. And so we're very happy to be going to Prague. And then next year in July, we're closing the project, and we will have then final delivery of the complete data portal, and hopefully the European Environmental Data Cube will be 90 or 100% complete by then. So it will contain all the data you might need for analysis or spatial modeling. So this is it from me. I don't know what else to say. I wish you, the ones that came to Wageningen, I wish you a safe travel back. I wish to stay in contact with you. You see, we're doing lots of development. We also have other projects. Always feel welcome to visit us at OpenGeo Hub. We also take guest researchers. We have a place for guest researchers. So you just talk with us, and we can provide a table, and then you can interact and collaborate. Yes, we are looking forward to the next year. There's a lot of exciting development. You see the Earth observation arena is exploding. There's more and more Earth observation data coming. The data science is becoming more accessible. The computing is becoming more efficient. The computers cost less. So it will be just more and more and more of data science. And that means that we have to get better and better in statistics. We have to get better and better in also our fields, understanding ecology, agronomy, meteorology, forestry, natural hazards. So we also have to get better in that because we want to do seamless modeling. So I wish you all the best also with your work. We stay in touch. I usually say in the summer schools, I say to PhD students, I see you in the literature. So we see you a bit in the literature on the conferences. Lots of conferences are coming back next year. I think the Living Planet conference will be physical. They're hoping, right? When is that one? In Bonn in April, so Living Planet, a huge conference, 1 week. Then the other is the Phos4G. This is next year, where? In Florence, physical one in Florence, end of September next year, Phos4G. If you have some announcements you would like to make, please, the best use the Mattermost. On Mattermost, there's about 120 people. So there's 120 people on the Mattermost channel of Open Data Science. And so if you want to announce some event, please use the Mattermost. You can still ask questions. And also I would like to say that from next week, Valentina, Ryan, and Chris, they will start editing all the videos. It takes about 2 weeks. It's a lot of work, but they edit the videos and they will prepare final videos. Then they uploaded to this German hosting platform, and then the videos become available with the DOI and with a little abstract. There's some people from also saying thank you very much. I had the honor to attend these 5 days. I'm Manali Drizi from Morocco. Yes, we're very happy to have also people from outside Europe on the transition joining. We're very happy to have you. And also I noticed there were some people watching from Latin America and from US. And so we're very happy to have people also beyond Europe, because this is kind of a European data science, but we support some people from India, I see. So we support also your open data science activities. So we are not exclusive, geographically exclusive. We call it Open Data Science Europe because it's you work with the European data, but we also have global projects and we like to collaborate with you very much. So please, good luck with your work. As I said, we stay in the touch. See you in the literature, see you in conferences. Come Phos4G, come to USAR, come to the Living Planet. EGU, I'm not sure anymore. I think they asked for too much money for too little. I'm also not sure about a couple of conferences, but USAR, Phos4G, absolutely recommend. So please come and network. And for those of you, one more time, have a safe travel back